this session, let us talk about monotonicity. Monotonic functions are of four types: strictly increasing functions, strictly decreasing, non-increasing, and non-decreasing. The discussion on monotonic functions is very important to us in calculus, and applications of this are also useful to us in various chapters of algebra, especially in quadratic equations. Monotonic functions, strictly increasing function, strictly decreasing function, non-increasing function, non-decreasing function. This discussion also helps us in solving many inequalities. Let us see what a strictly increasing function is. A strictly increasing function, it is behavior of a function in a certain interval. So, we need to know whether a function is strictly increasing or not in a certain interval, let us say an interval I. A function is said to be strictly increasing in an interval I, increasing in an interval I, if and only if for all x1, x2 belonging to I, let us say there are any two elements in the interval I, x1 and x2, for all x1, x2 belonging to I, f of x1 greater than f of x2 should imply x1 is greater than x2. A function f of x is said to be strictly increasing in an interval I if and only if for all x1, x2 belonging to I, f of x1 greater than f of x2 should imply x1 greater than x2. And also for any two numbers x1 and x2 belonging to I, x1 greater than x2 should imply f of x1 greater than f of x2. So, this is a by implication. So, a function f of x is said to be a strictly increasing function in an interval I if and only if for all x1, x2 belonging to I, f of x1 greater than f of x2 implies x1 greater than x2. For example, let us look at the function f of x is equal to sin x, and that too in an interval 0 to pi by 2. So, our target is to discuss monotonicity of the function f of x is equal to sin x in the interval 0 to pi by 2. Take any two abscissa x1 and x2. We can see x2 is to the right of x1. So, x2 is greater than x1. Now, if this is to be a strictly increasing function, then f of x2 has to be greater than f of x1. F of x2 is y coordinate of this point and f of x1 is y coordinate of this point, and you can observe from the graph that y coordinate at x2 is much greater than y coordinate at x1. So, f of x2 is greater than f of x1. Likewise, you take any combination of x1 and x2, x2 greater than x1, that is x2 to the right of x1 implies y coordinate at x2 will always be more than y coordinate at x1, or f of x2 will always be greater than f of x1. Such functions, they are called strictly increasing functions. So, whenever you are taking this definition to numericals, if you know that a function is strictly increasing, if it is given that a function is strictly increasing, or you know that a function is strictly increasing, then over an inequality you can apply the function or remove the function. If you know that a function is strictly increasing, or if it is given that the function is strictly increasing, then over an inequality you can happily apply the function or remove the function. I will tell you in a simpler words. Let us say we know that f of x is an increasing function. In interval I, and it is also given that x1 and x2, two numbers which belong to I, satisfy x1 greater than x2. It is given that x1 and x2 are two numbers belonging to the interval I, and it is also given that x1 is greater than x2. Now you can say f of x1 will be greater than f of x2. So once we know that f is a strictly increasing function, we can apply f over an inequality. For example, log x to the base e is a strictly increasing function. Log x to the base e is strictly increasing function. We know that 3 is greater than 2. So we can say log 3 to the base e will always be greater than log 2 to the base e. We know that within 0 to pi by 4, between 0 to pi by 4, sin x will be smaller than cos x. Sin x values are smaller than the values of cos x. And we also know that log is a strictly increasing function. So I can apply log on both sides of the inequality, and I can say log sin x to the base e is always less than log cos x to the base e. Likewise, we can also remove a strictly increasing function from an inequality. For example, let us say we know that cos x is increasing function in certain interval. We are given that cos x is increasing function in certain interval, and it is also given that cos x1 is greater than cos x2. It is given that cos x1 is greater than cos x2. Now we can remove cos on both sides and say x1 is greater than x2. Cos x1 greater than cos x2 implies x1 is greater than x2. So this way the discussion of monotonicity is helpful to us in solving many inequalities. Now let us see how to investigate whether a given function is strictly increasing or not. For a strictly increasing function, to investigate whether a function is strictly increasing or not, first approach is graphical approach. Let us recollect the definition in a mathematical sense. If x1 greater than x2 implies f of x1 greater than f of x2, then we are saying that the function is strictly increasing function. X1 greater than x2, if it implies f of x1 greater than f of x2, then we are saying that the function is strictly increasing function. So on a graph, x1 greater than x2 implies x values, we plot them along x axis, there will be abscissa of points on the graph, and f of x values will be along the y axis. So f of x1, a function is said to be strictly increasing if and only if x1 greater than x2, whenever x1 is to the right of f x2, y coordinate at x1 should be more than y coordinate at x2. F of x2 and f of x1, when we compare, f of x1 should always come out to be more than f of x2. Such a function, it is called strictly increasing function. So you can see, whenever x1 is greater than x2, if f of x1 is greater than f of x2, then such a function, it is called a strictly increasing function. So graphically, in simpler words, if you are moving along the graph along positive x axis and you are rising upwards, that you are moving along positive y axis, in such case the function will be a strictly increasing function. If you are moving along the graph in towards positive x axis and you are rising upwards, that is moving along positive y direction, then such a function, it is a strictly increasing function. So let us look at graphs of some functions, elementary functions, and see their monotonicity in particular intervals. Let us look at the graph of e power x. E power x, as x tends to minus infinity, e power x will be close to 0. So it will be tending to 0, asymptotic with x axis, and as we increase the values of x, at 0 it will be 1, and as x tends to infinity, it tends to infinity. Now, along this graph, start moving along positive x axis. This is our positive x axis. So, when I start moving along positive x axis, you can see I am rising upwards. That is, my movement is along positive y direction. When I am moving along positive x axis, the y coordinates, they are incrementing. We are rising upwards. We are moving in the direction of positive y axis. Such a function, it is strictly increasing. So, e power x we can say is strictly increasing on r. E power x is strictly increasing on r. Let us look at a different function. Let us look at f of x is equal to x square plus x plus 1, a quadratic function. We know a lot of things about this function. This is a irreducible quadratic, its discriminant is negative, and minimum value of this function will be at x equal to minus b by 2a. So, we can write this as x plus half whole square plus 3 by 4. X square plus x plus 1 can be written as x plus half whole square plus 3 by 4. So, least value will be getting when x is minus half. And how much is that least value? When I put x equal to minus half, this is 0, and this number, it is 3 by 4. So, y coordinate will be 3 by 4. As we increase the values of x from here, this is how the graph would be, a parabolic graph. Now, I start moving from in the graph along positive direction of x axis. You can see as I move along positive direction of x axis, I am coming down. I am coming down till this point. And from this point, when I move along positive direction of x axis, I am rising upwards. So, we can say this function is increasing from minus half to infinity. This function is strictly increasing from minus half to infinity. So, a function need not be strictly increasing throughout its domain. It can also be strictly increasing in part of its domain. So, this function is not strictly increasing on r. It is decreasing from minus infinity to minus half and increasing from minus half to infinity. Let us look at a different function. Another example. Let us look at the function f of x is equal to sin x. Let us plot the graph of sin x. At 0, sin x is 0. At pi by 2, it becomes 1. At pi again, it becomes 0. It is a odd function. So, we see this part is image with respect to origin. Now, let us move from minus pi by 2 to pi by 2 in the positive direction of x axis. I will move along the graph from minus pi by 2 to pi by 2 along positive direction of x axis. So, when I am moving along the graph, I am rising upwards. So, we can see the function is increasing from minus pi by 2 to pi by 2, and from pi by 2 to 3 pi by 2, when I am moving along the graph, I am coming down. So, this is a decreasing function. Again from 3 pi by 2 to 5 pi by 2, when we are moving along the graph, we are rising upwards. So, wherever we are rising upwards, it is a increasing function. So, it is increasing from minus pi by 2 to pi by 2, and it is increasing in the interval 3 pi by 2 to 5 pi by 2. It will also be increasing in the interval 7 pi by 2 to 9 pi by 2, so on. So, in general, we can say the function is say increasing in the interval minus pi by 2 to pi by 2 in every interval of length 2 pi. So, to write the general solution, we can add 2n pi. The function is increasing from in the interval 2n pi minus pi by 2 to 2n pi plus pi by 2. In every interval of the form 2n pi minus pi by 2 to 2n pi plus pi by 2, f of x is equal to sin x is a strictly increasing function. Let us look at another example. Look at the graph of f of x is equal to cos x. Look at the graph of f of x is equal to cos x. At 0 we know cos x is 1. It comes down to become 0 at pi by 2. It's an even function, so we see symmetry about y axis. This is how the function will be. Cos x is also a periodic function with period 2 pi. So, let us see. This is minus pi, 0, pi, 2 pi. Now, when I move along the graph in positive direction of x axis, I keep rising upwards from minus pi to 0, and from 0 to pi when I move, I am coming down. From pi to 2 pi if you move, you will again be moving upwards. So, from minus pi to 0, function is a strictly increasing function. Again from pi to 2 pi, the function is a strictly increasing function. So, in general we can say, as the function is increasing from minus pi to 0 and the function is periodic with period 2 pi, we can say 2n pi minus pi, 2n minus 1 pi, 2n pi plus 0, 2n pi. The function is increasing in every interval of form 2n minus 1 pi to 2n pi, that is odd multiple of pi to even multiple of pi. In all intervals of such form, the function is a strictly increasing function. We can see from pi to 2 pi, it is a strictly increasing form. Odd multiple of pi to even multiple of pi. From 7 pi to 8 pi, the function will be strictly increasing. And from even multiple of pi to odd multiple of pi, the function will be a strictly decreasing function. Let us look at another example. Let us draw the graph of y is equal to log x to the base e. We know the graph from elementary functions. At 1 log x becomes 0. As x moves closer to 0, log x tends to minus infinity. When x is infinitely large, log x is infinitely large. So, log x, this is how the graph is. Now, if I start on the graph and start moving along positive x axis, I keep rising upwards. So, we can say this is a strictly increasing function in its domain, and domain of log x is open interval 0 to infinity. So, in open interval 0 to infinity, log x is a strictly increasing function. And here we can also discuss a very important result on strictly increasing functions. We already observed the nature of e power x. Y is equal to e power x. When we saw the graph moving along positive x axis, the graph was rising upwards. So, this was a strictly increasing function on R. And y is equal to log x to the base e. Now, we see it is also a strictly increasing function. And e power x and log x, we know they are inverse functions of one another. So, we can say if f of x is increasing, f inverse x will also be increasing. If f of x is a strictly increasing function, then f inverse x will also be a strictly increasing function. We will discuss this result in detail later. Just this is an observation for now. Another example, let us look at the function y is equal to tan x. Draw the graph of the function y is equal to tan x. We know tan x is a odd function, periodic with period pi. At 0, tan x becomes 0. As x tends to pi by 2, tan x tends to plus infinity from the left side, minus infinity from the right side, 0 at pi, odd function. So, odd symmetry about origin. This is the graph of tan x. Now, tan x, if I start from minus pi by 2 and start moving along the graph in positive direction of x axis, I keep rising upwards. So, we can say tan x is a strictly increasing function from minus pi by 2 to pi by 2. And because minus pi by 2 and pi by 2 are not part of the domain, we have to put a open interval. So tan x is increasing from minus pi by 2 to pi by 2. Tan x is also increasing from minus 3 pi by 2 to 3 pi by 2. But in the combined region of minus pi by 2 to 3 pi by 2, we can see tan x is neither an increasing function nor a decreasing function. For example, take x1 here and x2 here. x1 is greater than x2, x1 is to the right of x2. F of x1 is positive, f of x2 is negative. So we can happily say f of x1 is greater than f of x2. So x1 greater than x2 is implying f of x1 greater than f of x2 in this region. But if I take this entire region, let x2 be a point here, x1 be a point here. x1 is greater than x2, but f of x1 is not greater than f of x2. f of x1 is negative and f of x2 is positive. So f of x1 is not greater than f of x2. So it is not a increasing function in the combined region. It is only increasing from minus pi by 2 to pi by 2 and again increasing from pi by 2 to 3 pi by 2. And because of this infinite discontinuity in between, it is not a strictly increasing function in the combined region. It is increasing from minus pi by 2 to pi by 2. It is again increasing from pi by 2 to 3 pi by 2. It will again increase from 3 pi by 2 to 5 pi by 2, so on. So in general, we can say tan x will be monotonic from n pi minus pi by 2 to n pi plus pi by 2. Tan x is periodic with period pi. So in the general version, add n pi minus pi by 2 to n pi plus pi by 2, tan x will be a strictly increasing function. In the similar lines, we have the definition of strictly decreasing function. A function f of x is said to be strictly decreasing if and only if a function f of x is said to be strictly decreasing if and only if x1 greater than x2 implies f of x1 less than f of x2. If x1 greater than x2 implies, this is also a by implication, f of x1 less than f of x2, then such a function it is called strictly decreasing function. A function f of x is said to be strictly decreasing if and only if x1 greater than x2 implies f of x1 less than f of x2. Again, when it comes to numericals, let us see how we can use this definition to solve numericals. When we know that a function is strictly decreasing, you can apply the function over an inequality by reversing the sign of the inequality. Let us say a function g is given to be strictly decreasing. A function g is given to be strictly decreasing. And we also know that x1 is greater than x2. It is also given that x1 is greater than x2. Now we can say g of x1 will be less than g of x2. We have to reverse the sign of the inequality. G of x1 is less than g of x2. Similarly, if it is given that f is a strictly decreasing function, let us say it is given that f is a strictly decreasing function, and it is also given that x1 is less than x2, let me apply a decreasing function. Whenever I am applying a decreasing function on an inequality will reverse. F of x1 will be greater than f of x2. And not just applying on an inequality, you can as well remove a decreasing function from an inequality, but again by reversing the sign of the inequality. Let us say h is a decreasing function, h is a strictly decreasing function, and we know that h of x1 is less than h of x2. From this, we can remove h on both sides and we can say x1 will be reverse the sign of inequality greater than x2. x1 will be greater than x2. So this is how we can apply or remove a strictly decreasing function from an inequality by changing the sign of the inequality. Simplest example of a strictly decreasing function is f of x is equal to minus x. F of x is equal to minus x. Let us plot the graph of minus x. Minus x we know is a straight line. Slope is minus 1, that is inclination 135 degrees and passing through origin. So, this is the graph of y is equal to minus x. Now, when I start from anywhere on the graph and start moving towards positive direction of x axis along the graph, you can see my finger comes down. We are moving downwards. So, we can say this function is strictly decreasing function. So, graphically a function will be strictly decreasing function when you move along positive x axis and you come down, then that function is a strictly decreasing function. So, y f of x equal to minus x is a simple example of strictly decreasing function. That is the reason whenever you are applying this function, that is whenever you are multiplying with minus sign on an inequality, inequality reverses. We know that 2 is less than 3. So, when I apply f of x, that is when I multiply with minus sign, minus 2 will be greater than minus 3. So, this is the simplest version of usage of an strictly decreasing function. Let us look at many other graphs and application of strictly decreasing functions. Let us see the graph of y is equal to sin x. Y equal to sin x is a decreasing function from 3 pi by 2 to 3 pi by 2. As you see, when we are moving from pi by 2 to 3 pi by 2 in positive direction of x axis along the graph, we are coming down. So, it is a decreasing function. Let us say we know that x1 and x2 are two numbers in the interval pi by 2 and 3 pi by 2. Let us say x1 and x2 are two numbers in the interval pi by 2 and 3 pi by 2, and it is also given that sin x1 is greater than sin x2. It is also given that sin x1 is greater than sin x2. Now, in this interval pi by 2 to 3 pi by 2, because sin is a decreasing function, we can remove sin on both sides and conclude x1 will be less than x2. The inequality will reverse, the greater than will become less than now. So, sin x1 greater than sin x2 implies x1 less than x2. So, that is how we can conclude from sin values the values of the transitive relation between values of the function. Let us look at another function. Y is equal to cos x, and let us say x we know that belongs to 0 to pi. X we know that belongs to 0 to pi. Solve cos x is greater than half for all values of x belonging to 0 to pi. Let us say we want to find all those values of x for which cos x is greater than half. This is the graph of the function. Cos 0 is 1, cos pi is minus 1. So, from 0 to pi cos x is a decreasing function. From 0 to pi cos x is a decreasing function, and half is cos of pi by 6. Half is cos of pi by 3. So, we have cos x is greater than cos pi by 3, and cos is a decreasing function. So, we can say x should be less than pi by 3. X should be less than pi by 3. So, when we are writing the solution set, from the given information x has to be less than pi by 3, and we are solving only in the interval 0 to pi. So, cos x should be greater than 0 and less than pi by 3. So, solution set is 0 to pi by 3 open interval. So, this is how we can use the discussion of strictly decreasing functions in solving inequalities. Then we have the definition of non-decreasing function. A function f of x is said to be non-decreasing in an interval I if and only if x1 greater than x2 implies f of x1 greater than or equal to f of x2. A function f of x is said to be non-decreasing in an interval I if and only if x1 greater than x2 implies f of x1 greater than or equal to f of x2. So, if you look at a graph of a non-decreasing function, either the graph can go up or it can remain constant for a while. This is how graph of a non-decreasing function will be. Either the graph will rise upwards as you move along positive direction of x axis, or it can still remain equal to for a point in time. Here we cannot use a by implication because of this equality. It is a simple straight implication. A function f of x is said to be non-decreasing in an interval I if and only if x1 greater than x2 implies f of x1 greater than or equal to f of x2. Then we have the definition of non-increasing function. A function f of x is said to be non-increasing in an interval I if and only if x1 greater than x2 implies f of x1 is less than or equal to f of x2. A function f of x is said to be non-increasing in an interval I if and only if x1 greater than x2 implies f of x1 less than or equal to f of x2. If you look at the graph of a non-decreasing function, this is how we can have a graph of a non-decreasing function. As you move along the positive side of x axis, either you come down, remain at the same level, or again come down. Let us now discuss the role of derivatives in discussion of monotonicity. The role of derivatives in monotonicity. Now, we usually find across a statement, if f dash x is greater than 0, then function is strictly increasing. If f dash x is greater than 0, then function is strictly increasing. This statement is absolutely true. If f dash x is greater than 0, then function is strictly increasing. But many children misinterpret it to be if and only if f dash x greater than 0, then function is strictly increasing. This is absolutely wrong. For a function to be strictly increasing, there is no necessity that f dash x needs to be greater than 0. F dash x may not even exist at all. There are many discontinuous non-differentiable functions which are strictly increasing in nature. So, for discussion of strictly increasing, not always f dash x will be useful to us. It is only in some cases, especially in discussion of differentiable functions, we need derivatives to talk about increasing or decreasing nature of the function. So, this we have to be clear before starting the discussion of monotonicity in terms of derivatives. So, the right way of picturizing the statement is a continuous differentiable function so only when a function is continuous and differentiable, we will bring in the role of derivatives in monotonicity. Whenever the function is either discontinuous or continuous but not differentiable, in these cases it is advisable not to bring in the role of differentiation unless you are thorough with the total concept. Now, let us understand from the graph of the function, whenever we are moving along positive direction of x axis, we are rising upwards, that is whenever x2 is greater than x1, f of x2 is greater than f of x1. That is, slope of this chord is always non-negative. Slope of this chord is always non-negative. And as we know, derivative at any point is limit of a secant, limit of slope of a secant. The derivative at any point will also be non-negative. Derivative at any point on the strictly increasing function will always be non-negative, but this is applicable only for differentiable functions. So, let us generalize this. A differentiable function is strictly increasing if and only if f dash x is greater than or equal to 0, f dash x is greater than or equal to 0 in an interval I, and that equality not forming an interval. We have to be very careful with the treatment of that equality. A differentiable function is strictly increasing if and only if f dash x is greater than or equal to 0 in an interval I, and that equality is not forming an interval. If f dash x is equal to 0 in an interval, in that interval we will get a constant region and the function is no longer a strictly increasing function, it becomes a non-decreasing function. So, f dash x can be 0, but it can be 0 only at a discrete set of points. Let us prove this. F dash x by definition is limit extending to a f of x minus f of a divided by x minus a. F dash x is limit extending to a f of x minus f of a divided by x minus a. Let us not get into much of technicalities, let us simply understand the proof. Extending to a includes the right hand limit as well as the left hand limit, limit extending to a plus as well as limit extending to a minus. We know that the function is differentiable, that means limit extending to a plus exists and is finite, limit extending to a minus exists and is finite, and both of them are same, equal. Limit extending to a plus means x is slightly greater than a. So, x is slightly greater than a makes x minus a in the denominator positive. And we know that the function is strictly increasing, and x is greater than a implies from the definition f of x is greater than f of a. So, if it is known that f is increasing, x greater than a implies f of x is greater than f of a. So, denominator is positive, numerator is positive, so the ratio is positive and the limit will come out to be non-negative. Limit of a positive function will always be non-negative. So, we can say right hand limit is non-negative. And let us also look at left hand limit. X tending to a minus means x is smaller than a. X is smaller than a and f is increasing function makes f of x smaller than f of a. So, numerator is negative, f of x is smaller than f of a. Denominator is also negative, x is smaller than a, and ratio is positive, and limit of a positive function will always be non-negative. So, in either of the cases we have f dash x to be non-negative. So, f of x is increasing implies f dash x is always greater than or equal to 0. F of x is increasing implies f dash x is greater than or equal to 0. So, we should never miss out that equality. Parallelly, remembering that equality should not form an interval. Let us look at a small application of this. Find all possible values of A such that f of x is equal to x cube plus 3x square plus ax plus 4 is strictly increasing on R. Find all possible values of A such that f of x is equal to x cube plus 3x square plus ax plus 4 is strictly increasing on R. Now, this is a continuous and differentiable function. All polynomial functions are continuous and differentiable on R. So, this is a cubic polynomial, it will be differentiable on R. And because this is a differentiable function, for it to be strictly increasing, it is necessary and sufficient that f dash x is greater than or equal to 0. So, for the function to be strictly increasing, it is necessary as well as sufficient that f dash x is greater than or equal to 0. This implies, differentiate the function 3x square plus 6x, let me take 3 common, plus a should be greater than or equal to 0. Now, we have a quadratic whose coefficient of x square is positive, and we want this to be greater than or equal to 0. So, for that this has to be a perfect square. Its discriminant should be greater than or equal to 0. It starts becoming a perfect square when a by 3 is 1, and from there on it will be perfect square plus some positive number. So, this will always be greater than or equal to 0. For it to be equal to 0, minimum value to be equal to 0, this has to be a perfect square, that is when a by 3 is 1, and for it to be strictly positive, a by 3 has to be greater than 1. Or we can say, because coefficient of x square is positive, for the quadratic to be entirely greater than or equal to 0, discriminant has to be greater than or equal to 0. Solving which we have a by 3 is greater than or equal to 1, or a is greater than or equal to 3. So, for all values of a greater than or equal to 3, we have this function to be strictly increasing function. So, if we miss out that equality, we will be missing equality here. Our answer would become open 3 to infinity, whereas the right answer is closed 3 to infinity.